All right, let's talk briefly about cis-trans isomers as it relates to alkenes. So we say cis is going to be on the same side of the double bond. Okay, trans is the opposite side of the double bond. So you might be asking yourself, what same of the double bond or what opposite of the double bond? So let's look at an example of an alkene. Okay, so in order to have cis-trans notation, this is very important. For cis-trans notation, okay, we want to have two equivalent atom or atom groups on adjacent carbons that contain the double bond. All right, so keep in mind that the hybridization of these carbons are what? sp2. So any atom or atom group that's attached to it is going to make this molecule flat with respect to the groups attached to the sp2 carbons. Okay, so if we draw a line that bisects, this is what you need to do. You need to draw a line like this, or a dashed line, however you want to do it, that bisects the left and right sp2 hybridized carbons within that double bond. Okay, now I need to make sure that I have an equivalent atom or atom group that's on the left carbon that's also on the right carbon. Well, let's look and see what we have. I have the CH3 group that's on the left carbon, and I have a CH3 group that's on the right carbon. Okay, so on the side of the double bond, the CH3 on the left carbon is in that direction, and the CH3 on the right carbon is that direction. So those two directions oppose each other. So we would call this a trans isomer. Okay, we can actually name it. Let's number it correctly here and say this is carbon 1, 2, 3, 4. So we have a 4-atom system. We have trans dash 2 chloro, and that 4-carbon system is going to be 2 butene. Okay? Or we could call it trans dash 2 chlorobut 2-ene. Either name is acceptable. But the main point is for cis-trans notation, we have to have identical atoms or atom groups on the adjacent carbons, the left and the right, that contains the double bond. Okay? Let's do another example. So, if you have a question on the exam that says name the following molecule with cis-trans notation. All right. Now, let's say we have a structure like this. Carbon, doubly bonded to carbon. And what's attached to this carbon is a CH3, an H. What's attached to this carbon is a CH2, CH3, and an H. All right. Now, the first thing we want to do to examine cis-trans notation, if we do indeed have it, we want to draw a line bisecting that double bond. We want to write left side, right side. And it's with respect to these two carbons that are in the double bond. Now, I want to look at each carbon and I want to see, do I have an equivalent atom or atom group that is on the left and the right carbon? Well, guess what? We do have one. Okay. The H is projected that direction. That H is projected that direction. And since they are projected in the same direction, or they are on both sides of the double bond, same side of the double bond, we're going to call that as cis. Okay. Now, what is the name of the molecule? For naming purposes, let's number. We want to go the shortest route to get to the double bond. So that's 1, 2, 3, 4, 5. And that's going to give me cis 2, 5 carbons. That's going to be a pentene. Or we can call this cis dash pent dash 2-ene. All right. Now, one thing we also need to keep in mind, this is a Lewis structure with some condensed terms on it. We need to be able to convey this Lewis structure into a line angle structure. Okay, so if I erase this for now and I want to represent this entire thing as a line angle structure. So what you want to do is you want to make your double bond, and this would be the CH3 coming off. Here I would have a hydrogen, and that would be a CH2. This would be a CH3, and this would be a hydrogen. Okay, let's look at our numbering and see, is our numbering correct? 1, 2, 3, 4, 5. Everything corresponds. All right, this may be a little messy. but this would represent that CH3. This would represent that CH2. This would represent that carbon. This would represent that hydrogen. Over here, that would represent that CH3, and over here, that would represent that hydrogen. Okay, so this is the exact same thing we did in chapter 1, going from these expanded Lewis structures and condensed structures into a line angle. You have to be able to transpose one into the other. You have to be able to recognize one and be able to visualize and draw the other. Okay? Now, if I talk about cis-trans, in another context, let's look at another example of cis-trans. And this example is going to be unique because it's going to lead us to something that actually conflicts the name when we get to the EZ nomenclature. Okay? So let's say we have a carbon-carbon double bond, and we have a CH2 here, and a CH2 here, and a CH3. Okay? And I'm going to bond this carbon to a CH2, CH2, CH3. Okay? So let me smooth. Now, I'm going to have a hydrogen here and a hydrogen here. Now, the only criteria we have for cis-trans notation is going to be, let me draw my line that bisects my left sp2 hybridized carbon and my right, because this is what we're looking at, what's actually attached to those two carbons. Now, is this a cis-trans isomer? Well, the criteria is that we have the same two atoms or atom groups on both sides of the double bond. So that is true because I have a CH3, CH2, CH2 here. I have the same group here and the same group here and the same group there. So these two are the same and those two are the same. So I meet the criteria for cis and trans. I have two groups that are the same on both carbons, but if I had one group, I would meet the criteria. So yes, it is. Okay, now what if I change this H to a Cl? What if I change that H to a Cl? Is this still a cis-trans isomer? Well, yes it is, because on my adjacent carbons across the double bond, these two groups are the same. The hydrogen and the chlorine are not the same, but these two groups are the same on my sp2 hybridized carbons. So this does qualify for a cis-trans system. Okay, so we can actually name this. Let's see, this would be carbon 1, 2, 3, 4, 5, 6, 7, 8. So we see both similar groups projected on the same side of the double bond. So we would call this cis. And we have a chlorine on carbon 4. So this is cis 4 chloro. And we have 8 carbons. And the double bond appears where? Between carbon 4 and 5. So that's going to be 4 octene. So cis 4 chloro 4 octene. Okay. Now this example is an example I will use when we talk about easy notation, and the fact that it is cis, but it will defy another rule that we will look at. Okay. But for the purposes of the cis-trans convention, that molecule is cis. Okay. Now let's look at another example. Is this molecule a cis-trans isomer? So if I do C, bind it to C, I'm going to put H, CH3, CH2, CH3. Is this a cis-trans isomer? Well, let's look. Okay. No, it is not. On the left, I do not have an atom group that appears on the right. I have 2 hydrogens here and a CH2, CH2, CH3, and a CH3 over here. So I could not use the cis-trans notation with that. Indeed, we can name this. Let's see how we would name it. Okay. Keep in mind our rules that we want the smallest number for the double bond. So we need to go across the double bond from 1 to 2 or 2 to 3 and so on. So this would be 1, 2, 3, 4, 5. Okay. So that would be my longest chain. So we would have pentene. And you could also call it 1-pentene. Or you could call it pent 1-ene. But since the double bond occurs on the first carbon, it's understood to be on number 1. That's why we simply use pentene. Okay? So what we have is a 2-methyl pentene. The CH3 group is coming off of 2, and we call this 2-methyl pentene. All right, we could also call it 2-methyl pent 1-ene. Okay, now how would we draw this expanded Lewis structure, expanded Lewis / condensed structure as a line angle structure. How would we do that? We would have a double bond, CH2, CH2, CH3, and we would have a CH3 like that. Okay? Now let's number our hydrogen. This would be 1, 2, 3, 4, 5, like that. Okay? This is your CH3 group. Now, what is understood, if I leave these two lines terminal with nothing on it, this is understood to be a carbon with two hydrogens. You have to remember that from chapter 1. Okay? This is understood to be your carbon here. Okay? So this whole thing, let's use another color. This whole thing is represented by this. Okay? And this CH3 is represented by that. And this carbon will be represented by that. This carbon will be represented by that. This hydrogen will be represented by that, or left blank, or that hydrogen will be represented by that, or left blank. You have to realize that that is the exact same structure as this and this. Okay? All right. So this is how far we can go with cis-trans isomers. And we need to know that it only works for simple systems. And you must have something that is at least disubstituted. We'll talk about substitutions in a following video. But it only works for simple systems, and we don't use it very often. You do not use it very often, but you need to be aware of what it is, and you need to be able to identify it.